Okay, folks, we're going to go and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please do the best you can to make sure your microphone is muted and your video's camera is off when you aren't intending to speak. It's my pleasure to introduce Scott Beeson today. Scott has served as the first park geologist at Mount Rainier National Park since 2010. And prior to this role, he also served at the NPS as an interpretation and law enforcement ranger. He obtained his master's degree in 2006 from the University of Northern Iowa, which is also his home state. His thesis focused on studying aggradation in proglacial rivers and the response of glacially fed rivers to a major storm that impacted Rainier. And his current research focus is on the genesis and fate of debris flows in the park, especially with respect to the ability to forecast and track debris flows as they move down valley. So Scott, I'm going to go ahead and let you take over. Thanks so much for being with us today.
All right, thank you, Matt. It's great to be here. I appreciate the opportunity to speak about some of the programs that we have going on here in the park. So I'm going to spend the next 50-ish minutes here talking about some of the forecasting and seismic detection of debris flows that we have going on at Mount Rainier. So again, today's talk, it would be a complete miss of me not to mention some of the USGS seismic upgrades that have been going on here at the park. We've been able to really piggyback on some pretty amazing work that's been going on thanks to the USGS. So talk about some debris flow history. The most recent Tahoma Creek debris flows that kind of really highlighted the issues that we have in the park here with debris flows. Talk about some efforts that we've made at forecasting debris flows to kind of better understand how they form and inform management of the park so that maybe we could close certain areas over time. And then talk about some initial steps and then some upgraded steps of debris flow detection systems using seismic data, and then have some conclusions in there. So there's a major caveat here is that I am not a seismologist. So I'm going to be talking about seismology stuff, and if you have some really detailed questions, I'm probably going to defer you to the people I've been working with at the USGS. So Wes Thalen, Seth Moran, Alex, everyone at the USGS that have really picked their brains big time. I really appreciate their work. And getting right into acknowledgments, I have to acknowledge my team, Robbie Taylor, Paul Kennard, who's retired, but really got me, started here at Mount Rainier back in 2006 doing the work on aggradation in park rivers. One of our major partners here in the park is the USGS Cascades Volcano Observatory, and this system, the current debris flow detection system, is heavily based on work that Wes Thalen has helped me with, and Seth Moran and Ben Pauk and others that have really worked on the HAR network expansions, which I'll talk about here in the next slide. Got to talk about the University of Washington Pacific Northwest Seismic Network as well. Carl and Doug, Brendan, Steve Malone, who is emeritus, but will definitely help with some of the things we've done in the past. University of Oregon has been doing some really cool deployments of seismometers in the Tahoma Creek Basin, and it's going to be really interesting to see the data coming back from them this year. And then one of our long-term partners, Claire Todd, she used to be from PLU, Pacific Lutheran University, but now she's out of Cal State, San Bernardino. So she has a couple, every year we put up cameras, time-lapse cameras, to see if we can capture debris flows, and I think we may have actually got one this year. So I'm really excited to get that data back. So first thing I want to mention is the seismic network that we have in Mount Rainier, because a lot of the system that we have is dependent on seismic networks. So this is how it looked in the 1980s. We had Longmire, which is where my office is here. I'm going to pull up this laser pointer device. So Longmire is here. This is Mount Fremont up in the north part of the park. There was two seismographs before the 1980s. As we move on, the 1990s, we get up to 5. We added the Emerald Ridge seismograph, which is one of the big ones that we talk about here on the south side of the park for debris flow detection. At Camp Sherman, and then I believe that's Voigt Creek up there on that side there. And then USGS comes in before the 2010s and adds in Observation Rock, Panhandle Gap, a couple more that get added in, St. Andrews Rock, which is a really fun one to get flown up to in a helicopter. We get into the 2020s, we get up the recognition of Lahar hazards, which are these large surface events that can go many, many, many miles down valley and have the largest effect of basically is the reason why Mount Rainier is such a hazardous volcano. The USGS has this recognition of this, and they start adding a much larger network. So this is as of 2020. You can see there's a large expansion of the network on the south or on the west side of the park and also on the south side, as well as kind of trying to get something on the east side like Ohana-Pikash, OPCH there. Really trying to expand this network. 2022, we added quite a few stations on the southwest side, and these are specifically looking for events that would go down this drainage here, which is the Puyallup River, and then down this drainage here, which is Tahoma Creek. So we really use a lot of these seismographs that are located in this area right here, specifically for the detection of Lahar, of debris flows. But again, this is a piggyback on the seismic network that is for Lahar detection and movement downstream. And then as it is right now, we've added 2 more stations. The USGS has added 2 more stations, including Kavik, K-A-V-K, which is named after my dog. So I asked Ben Pauk if I could name a seismometer, and he said yes. So I named it after my dog. So there's Kavik when she was a puppy at Ocean Shores. So it's just kind of a fun little thing. So we now have 34 seismometers in Mount Rainier, 7 PNSN, and the rest are USGS. Mount Rainier is probably one of the best seismically monitored volcanoes in the world now because of this network. And it's not complete. I think there's a couple more we could get in. I'm sure the USGS would say the same thing. So the motivation of what we're doing here at Mount Rainier is understanding that Mount Rainier is a big volcano. It's falling apart. It weathers. You have rockfall. You have debris avalanches. Glaciers carry all this material downstream, provides it to the zone of debris flows, which then move that sediment into rivers, and then floods carry that sediment outside of the park. There's some great quotes there from Bruce Barcott and then Gordon Grant. Mount Rainier's drowning in its own sedimentary drool, basically. And the background of that photo that you see there is from Tahoma Creek Campground, right as they closed it in the 1960s, late 1960s. So a lot of what we look at and a lot of what one of my interest is understanding how these surface events can affect infrastructure, how they can affect roads, trails, built environments, and trying to avoid placing infrastructure in these locations so that we can better provide access to people that are visiting the park, and also make sure people are not in the path of debris flows. So there's a rich history of debris flows in this park. I think the current number is somewhere in the range of about 60 that we have recorded from the 1930s. Or 1920s to the 1930s, all the way on to as late as this year. So the picture on the left here is the Nisqually Glacier with an outburst flood, interestingly coming over the top of the glacier. That leads to flooding in areas downstream, like where my office here is here in Longmire. And then just below Longmire, there's been areas where the road's been washed out because of these events. So we need to understand these so that we can, better protect our infrastructure and better protect our people that are visiting the park. So, and we've recorded these events. This was the very first iteration of some of the stream gauging we have in the park. Recorded an outburst flood that happened in October. Again, you can see kind of a really quick peak of about a meter of stream stage that increases. And interestingly, you look at the water temperature, which is that blue line. There's a dip in the water temperature, and that tells you have a water source, a glacier source for that water. So cold water emanating from a glacier that is then working its way downstream. So, we've seen these before, and there's a couple really interesting things about the environment here. With glacial recession and climate change, we're seeing huge areas of just an endless supply of sediment. Oversteepened sediment, you look at it the wrong way, it'll collapse. It's literally just deposited directly by the glacier, and it gets mobilized during these events. And this is, I believe this is a 2019 debris flow that we had down Tahoma Creek, and you can see these slopes on either side of the channel have been incised upon. Looking at this is the South Tahoma Glacier terminus right here. It doesn't really look glacial, but it is. But inside of this is all ice-cored moraine and material that is all very, very quickly picked up by debris flows. The picture on the right is from Nick Legg, who did some research looking at the sources of debris flows and kind of the genesis of them. Every debris flow that's initiated since 2006 has been in an area that's been recently deglaciated. So it's these sediment stockpiles that are being provided to the rivers that can then work their way downstream. It's remarkable how much sediment is available up there. There's a lot of text on this slide, but basically the thing to note on this is that there's not only sediment that's available, there's also water. And glaciers, this is a photo from CAM 1997 that was in Walder and Dreger. Actually, I think the date on CAM is wrong on that one. Now that I noticed that, I've got an error on the slide. But the figure on the left basically shows that the bottom of these glaciers are not smooth. So you get these cavities that form. Water can accumulate in these cavities, and when you get really, really warm, like weeks-long periods of warm temperatures, water can get into these cavities. Pressure increases, and all of them suddenly get into a tunnel system that can rapidly drain that water. And that's what we see in a lot of our events. And I'll have a video coming up here in a second. One of the things to watch for is how much water actually is coming out of these events, because we will see water in our stream after a debris flow that is much higher than what we had seen before. And I love this last comment. It's something I'm going to come back to a couple times. That a puzzling aspect of outburst floods in South Tahoma Glacier is that there's a few occurrences of hot weather or heavy rain that do in fact coincide with outburst floods. And this brings into the point that it's extremely, extremely hard to predict these events. So the best forecasting models we have still overpredict everything. And I don't know how we're going to get that fixed. But again, talking about subglacial hydrology is important in understanding this. So moving on, this is looking at some of the drainage basins. You have Couts. Most of these are on the southwest side. There's some on the north side here. But the number of events that are outburst floods, debris flows, which are most of our debris flows in the summertime start as outburst floods. So you could kind of make the argument that a debris flow is actually an outburst flood as a start. The unknown other category is these kind of weird anomalies that we see. We just had one this last weekend on Couts Creek. So I'll talk about that at the very end. Where we see something, I'm not entirely sure what it is, but there's something going on. But then you can kind of see the range and times in some of these. And again, 1926 to 2023, we average about 3 events every 4 years or so, about 3.2 events every 4 years. So, and this is all known events. There's some of the, looking back in the archives, it's really frustrating a couple times. You see where people will say, we had debris flows time to time throughout this summer. And it's just like, well, that does no good because we can't look at the antecedent weather to determine, what caused that debris flow. So one of the big points is if you're going to record things, actually record them. So we can come back and find data for it. So most of this talk is going to focus on South Tahoma Glacier and Tahoma Creek, just because it's the one that has by far had the most events, over 36 in that period of time there. So let's look at the South Tahoma Glacier. Again, it's southwest side of Mount Rainier. It's a small little glacier. I mean, it starts about 10,000 feet up here, ends about 7,000 feet down here. It feeds basically Tahoma Creek. Tahoma Glacier, confusingly, feeds the South Puyallup River, but there's this tiny little tongue of Tahoma Glacier that comes in here. Emerald Ridge seismograph is located right about here. I don't have it on here. Notice now, but Copper is around over here somewhere. Mildred Point is over here. We'll talk about some of these other ones here. But you can see we're really going to be focused on this glacier. And actually in the 1960s, 50s and 60s, the terminus of South Tahoma Glacier was down here. So all of this in this valley is really loose, unconsolidated material. Looking at the timing of debris flows, there's 2 different populations of debris flows that we see in the park. We have these dry weather debris flows where you get long periods of hot weather and then something will pop, the cork will pop, and then you get a surge of water and it quickly bulks up, turns into a debris flow. We also get the wet weather debris flows where you have like intense precipitation, and then that runoff then picks up material and bulks up and turns into a debris flow. So 2 separate populations of debris flows, which then gets into also the forecasting. You're trying to forecast one of 2 different types of varieties of debris flows. So when we get into that, I'll talk about why that can be a little bit more complicated. You can see there was a kind of a period where we had dry weather debris flows, a period where we had a lot of wet weather debris flows, and then we're kind of getting back into this maybe dry period of time where, maybe starting to see sediment that's loosening up on the upper mountain, and we're going to potentially see more debris flows as we go on here. But again, there's a distinct timing of these events. So between June, July, and through November is when we really see those. Don't really see them after about November because of the snowpacks that we get here at the park. So, And what does this do to infrastructure? This is looking down. So South Tahoma Glacier is up off this direction. This is Tahoma Creek as it comes down. This is the West Side Road. We used to have a campground sitting right here, which is that upper right picture. In the 1960s, it looked like this, and then 2006, before the 2006, our big flood of record, which I'm not really going to talk about, but was huge. This valley had widened significantly, and the cross valley gradient was amazing. And so it's easier for the water would rather go this direction than this direction. So it really puts infrastructure that we've built in this valley at risk. And you can see this, basically that lower right photo is taken right about here. And that's a roadway that's been damaged that we've actually since repaired, and it's in pretty good shape right now. So moving forward, we're going to look in 2015. Before 2015, I didn't have a huge interest in debris flows, kind of understood that they were something to be, to look into, but 2015 was the year that all changed. This is the snowpack we had in 2015, which was it was an abysmal year for snow. It was a winter without a winter. We're basically waiting for the snows to arrive, and they never really did. And it is the lowest snowpack recorded in recorded history, Mount Rainier. So August 13th, 2015 was the best day to be a geologist in Mount Rainier. About right around noon, I was eating lunch in my office, and one of the volunteers, and you can see the video in the background here, one of the volunteers was reported on the radio that there was a debris flow coming down the valley. And this was actually the third of 4 surges of a debris flow. This one actually made it down to here, to this location. You can kind of see along the West Side Road. But this is the end of this debris flow as it's losing energy. It's turning into, starting to deposit everything it's carrying. It's turning into more of a hyper-concentrated flow, but still a lot of energy in this location. So I remember talking to the visitor as we were coming up here, and it was just amazing. They were saying how loud it was, and we were actually up there just around the corner a little bit by the Tahoma Creek trailhead, so right about here, when the 4th debris flow surge went past, and there was zero doubt in my mind there was a debris flow going on. So we were able to get up in a helicopter, fly around, and you could see the lower left photo, this just huge areas of sediment that were incorporated in. We had up to 12 different hyperconcentrated flows that were recorded by people that were on the Tahoma Creek suspension bridge. As you would see an increase and see the flow go past their feet. It's pretty impressive. And we were able to go up and find the source of it, which is right up here in the lower part of the South Tahoma Glacier there. So you can find this video online. There's some really, really bad narration by the visitors. They're basically saying how scared they are. And they rightly are scared because they're in probably the worst place you could possibly be. Yep, that's right. Get closer to the event that's trying to kill you. They're in one of the worst places you could possibly be for a debris flow. So this really kind of scared me in the sense that we had people way too close to a debris flow. So looking at some of the data, the top line is the seismic trace. So you can see there was a small kind of clearing of the throat of the debris flow 2A and 2B, which we thought was one event until we looked at the seismic data, which is why we call it 2A and 2B. 3 was the biggest one that reached, that was the video where you could see where that reached there. And then 4 was the one that went past when we were up there. I'm going to talk about RSAM in a little bit, but RSAM is real-time seismic amplitude measurement. It's a tool the USGS has developed to on the way I think of it is to summarize seismic data. So that's a lot easier to see, to pick out the increase in seismicity of an area. It's more for volcano monitoring, but we were using it for a long time to do debris flow detection, and there's some good things and bad things about it. But again, you can see that the increases in these events really correlate nicely with the seismic. And then the last thing on here is really interesting is the soundscapes monitor. A completely independent effort Park Service was doing to look at the sound of the debris flows as they were going, or the natural environment as they were going by. They weren't expecting debris flows. But what was really interesting is around 8:30-ish in the morning, the river gets anomalously quiet. And if you look at this trend and you look at the 42-day average of the data we have, this was anomalous. This was something major going on. And it doesn't look much like it here, but you don't see this ever on this trend. And then you can see the individual surges going by. And then, as I mentioned, the river was noisy or was loud after it went by. So the suggestion on this data is that there's something that blocked the river and it was loud for a little while after that. So something really interesting going on there. And you can see, again, there's a debris flow deposit for sure in that location. Looking at some other data, I'm going to move through this kind of quick, just some other cool stuff we were able to get from this. So the channel shifted from basically to the south in this event and incorporated a lot of material in this location. Using DEMs of difference, we were actually able to see what this change was. I say this is still preliminary. I'm still waiting for the final data, even though it was a 2015 event. But you can see there's a definite scar where a lot of bulking occurred. And another interesting thing is looking at the glacier, how much actual change there was in 1 month. It was incredible. But in this little comma-shaped scar right here, about 15,000 dump trucks worth of material removed in a single event. Another debris flow we had in August 2019. This was as I was driving into the park. This is Tahoma Creek and Tahoma Creek Bridge. We can have discussions later about how misfit this bridge is for this channel. But you could see that this is the chocolate milk quality of this river. There's a ton of sediment in here. And if you were to actually smell the air, it smelled like Christmas trees. It smelled like fir trees smashing around, basically. We were able to determine there was another debris flow. Got to fly in a helicopter again. There's a trend. It's really fun to find helicopters when there's debris flows going on. So it's the best way to see what's actually going on. But you can see again this scar here. You can see how it's bulked up in this zone, and you can see more bulking here. And just see the quality of the water coming out of the glacier is just there's much more water coming out of these events after than there was before. And again, August 2019 shifted it even more. Yeah, I could update this slide and tell you that the current channel is over here right now after this latest debris flow we had this summer. So it's moved around quite a bit. So this gets us into forecasting. The intent of the debris flow forecast is to create a quantitative forecast for relative debris flow hazards. The predecessor who did geology before me would send out emails on really hot days and say, hey, it's really hot out, we could have debris flows today. And surprisingly, she was right most of the time. I don't know how, but she was right. I didn't really like the fact that it was quantitative or qualitative. I wanted it to be more quantitative. So we built this on a debris flow or a model of rain-induced debris flows by Nick Legg. So there's the wet versus dry forecast. We'll talk about those different sides. We use antecedent weather and forecasted weather conditions. So look at some of the higher altitudes weather stations we have in the park, and then a variety of different forecasting models. We run it every 4 hours, and it outputs a score, which is low to very high, and then that's for the wet and dry side, but then for dry forecast, there's a numeric score. And again, there's this caveat that it is incredibly hard to find common factors in previous debris flows, and so it's really hard to figure out one thing that leads to a debris flow. So there's actually a lot of different things that come out from these analyses. So looking at this is kind of a schematic of how the model works. Every day we look at the 18-day precipitation total. If it's greater than or equal to 4 inches, we go to the wet side of the model, which is, again, the stuff that Nick Legg worked on. Look at snow water equivalent at Paradise, so 5,400 feet, which is kind of similar to the terminus positions, a little lower than some of the terminus positions in the park, but that idea of what's it like at the terminus. Look at the average temperature and then these precipitation thresholds to get the score out of there. So depending on the snow water equivalent, depending on the temperature and the precipitation thresholds, you can get the score from there. I'm not going to spend a ton of time looking at this. If you have more questions about it, you can scan that QR code or you can ask me. We actually have published this in after a debris flow conference from a couple of years ago in Golden, Colorado. We published the way it works. The dry side is I consider it's more of a Monte Carlo approach, where we're looking at the things that are in common on days that have debris flows on the dry days. So we look at the maximum temperature and compare that over the maximum temperatures for those days and over time. I call that the Tmax percentile. Look at the date. The average meltout date is July 11th. So as you go later on, then you have less and less snow, so stuff becomes unstable. So that's kind of where that value comes from. We look at the 18-day cumulative heating, or temperature above 32. That's DD32. The 3-day precipitation, if there is any precipitation on top of that, you can destabilize that. And you look at snow water equivalent and then also high temperatures. So Walter and Dreger found that temperatures greater than 68 have a higher possibility of having a debris flow. So you get a score, and we've equated that with those color codes there, basically. So Goes into this model. I put this screen in last night, so this is what it would look like this week. Basically, we have enough snow up high right now, even though we're in the wet side, that it's going to take quite the event to melt that rain or melt that snow and produce a debris flow. So, and then again, we published this in the AEG, it was like a couple of years ago, 2021. So if you're interested in that paper, go and scan that QR code, or you can ask me later. I can send it to you. What it looks like, this is this year's results. Obviously, most of the year we don't have debris flows. And again, this model over predicts, and I will be the first one to tell you that. Again, we had 2 debris flows, August 15th, which was, right in this, it did predict a high score that day. And then November 4th, we had something, so it predicted it there in those days too. The real utility of this is for recognition of hazards and situational awareness. So people that are working in Tahoma Creek or recreating in Tahoma Creek, if they're out in these locations and they have these higher scores and they have the potential of recognizing that there is the potential of having an event. So that's really the big utility of this model, is that it's more of a recognition thing. It doesn't predict debris flows as best as it could. And I think that we'll never really get to that point unless we have a great understanding of the subglacial hydrology. So switching gears, we're going to now look at detecting debris flows in seismic data. And if you can do pattern recognition and pattern analysis, this is actually not too hard. Debris flows have a really common seismic signature that's really common. And again, I'm not a seismologist, but I've learned to be able to look at seismic traces and see something that doesn't look right. So again, here's a seismic trace. This is the August 2015 debris flow, and you can really see. I like to tell like the interp folks and other people that a debris flow is like a train approaching you on a train track. It gets really loud. It's loud for a while as it's passing, and as it goes away, it gets quiet again. So seeing that, and then looking down the RSAM trace below that, the first model that we used to predict debris flows was simply finding a trace or finding an RSAM signal that was higher than a certain amount, and that it was increasing in intensity over a certain amount of time. And that was like, I think on here, this is above, I believe, about 400 or 500 counts, increasing in intensity over 5 minutes. That was literally what the detection was before. And don't have to point out to me all the errors with this. I got numerous wind noise detections. I got numerous airplanes flying over, all sorts of things. It was a good first effort, but it didn't work very well. But the point of this is, we had the visitor or the volunteer that noted the debris flow about 12:02 p.m. Pacific time. If this system would have been in place, we would have been able to detect it by 5:20 p.m. or about 2 hours and 42 minutes before that. So 1720 UTC, 1902. So there's a pretty significant time gap there, where if we can detect an event, we can get people up there to evacuate the areas, sweep the areas, keep people out of the low-lying locations, so that we can then make sure that we're not going to have people swept downstream in a debris flow. It's the last thing I want to see. I do not want to see people in these locations when there's a surface event coming down at them. So we did this on 3 seismic stations: Emerald Ridge, RER, which is right here, looking at kind of these rivers, Longmire, which is the oldest seismic station in the park, kind of looking at these ones, and then Mount Fremont up here looking at these 2. It would output something that looked like this. Again, we could see seismic traces of a nearby earthquake. Again, I don't really care about those earthquakes. Just a regular trace there. And then you can kind of see the RSAM. So these are Emerald Ridge, Fremont, and Longmire, and you can kind of see just kind of what it looked like. It would turn red. The screen would turn red. It was a screen in my office. It would turn red and send me a text message if something happened. It worked pretty well. We actually did have a detection in 2019. And I remember this day really well because it was incredibly windy up high. And one of the things I'll mention, especially in the next one, next part of the system here, is that wind noise in Emerald Ridge there's something about that seismic station that it just detects noise, the wind noise really, really well. I don't entirely understand why, but the system would get tricked. The old system would get tricked by this. So again, you can see this is the seismic trace. This is the spectra, and I'm going to mention a lot about spectra here in a second. And then here's the RSAM, and RSAM2 is a filtered RSAM. So trying to get some of that wind noise out of there. And so spectra is really interesting in the sense that, you have the seismic data, but then it tells you a lot more about the signal and what's really going on. So spectra is what actually led to the next development of the system. So again, here's some debris flows. This is August and September of 2015. And when we actually look at the spectra, there you see a lot more. There's way more data here. So you can see kind of the shakiness of the seismic traces here, but you can see this increase in intensity across a large frequency range here. And you can see as the bigger events, the more intense the shaking is. And shaking may not be the best word, but you can pop this signal out really, really well. So here's August 2015, August 2019, and then September 2019, where we have the wind noise, which is this lower frequency and kind of a mirror of that at the upper frequency ranges. But there again is that signal that you can totally see. So what I did was basically try to figure out how can I desample this really complex spectra data into something that's really useful. And so what I did was kind of look at some of these events that have happened in the past. This is the August 2019 and then August 2015 and then August 2019 events here. And what I'm looking at is the frequency ranges, and kind of the red lines show you the bins that ended up using. So 0 to 2 really showed up wind noise extremely well. So I'm pretty much ignoring this. I'm pulling out a sample from here, 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 and here, and then putting it in 30-second bins. And so these plots or these graphs down here, or tables down here, are essentially interpretations of some of this data that's been averaged out. So my goal of all of this is to be able to go from this green, which is at alert level of 0, 1, 2, 3, to basically detect these events in a real time, and then try to get some sort of recognition of these and get people out of the areas that are affected. So what happens now is every 5 minutes, there's a Python script that downloads raw spectra values for each seismograph and saves it as a text file. And I have to thank Wes Thalen so much for providing me the scripts to do this, because it would have been impossible for me to learn it without that. So PHP is a web scripting language I'm really familiar with. I've used it for a long time. You could do the same thing in Python, but I use PHP because I'm more familiar with it. Basically, I take this spectra and I put it from a number that's really hard to use into a number that's a little bit easier to use, basically. I filter it into 30-second bins, so 0 to 2 hertz, 5 to 10, 10 to 15, and 15 to 19 hertz. I append those new values into the database, and you can see an example below that shows copper. There's a bunch of other stuff going on there. There's the start time, end time for that bin as a Unix timestamp. And then that filtered amplitude for that frequency range. Basically, FO205 amp is the amplitude for the 0205 frequency range in that bin. And then run the filtered value, look for a debris flow signature, essentially is what happens, and runs it through an alert level array, basically. And if an alert level is exceeded, a text message is sent. Put this system in place about, I think it was May or June this year. We already have 1.6 million data points, so a lot of data. Seismic data is incredibly, there's just so much data in this. This is the current alert levels. It's been tweaked several times, but basically, if we're seeing alert levels that are, less than 6 hertz, or the amplitude is less than 6, and again, don't ask me what the units are. Actually, I asked Alex at USGS that the other day. I'm like, I think it's a velocity, but I'm not entirely sure. Again, I'm not a seismologist. But if it fits into these bins, then an alert level is generated. And really what it's looking at is the minimum value that's observed in each bin over a 2.5 minute period of time. And that's hard to understand, but the next slide will make it a little bit easier to understand. And so again, this is the analysis of one of these data points. And you can see this is actually during one of the debris flows. 21.106 is the minimum. And if that were the minimum over the 5-minute period of time, you come back up here and you see that the event would be an alert level 3, and that's what that shows, alert level 3. So what we're looking at is kind of a window. So this is again looking at between like 10:13 to 10:15. This is showing 4 minutes. We've actually tweaked it to not 4 minutes, sorry, it's showing 2 minutes. We've tweaked it to 2.5 minutes. So what it's looking for is in each of these frequency ranges, the minimum, it gets an alert level and it gets the minimum alert level for this entire box. So at this time it was 0. As we move into this, you can see there's an increase in the amplitude across all frequency ranges. And this, at this point here, develops an alert level 1. Currently, alert level 1 is a possible event, and it sends me and a couple other people a notification. When it gets into 2, right now it sends like our dispatchers a notification and a bunch of other people, so that it gets more people excited, basically. So because I have a higher confidence that 2 and above are debris flows or something that at least needs to be investigated and get people out of the locations. So that's kind of the window of time. It's a pattern recognition over a window, and that's what it's really looking at doing. So currently, we use Emerald Ridge, this station, Copper Mountain, this station, Mildred, and Paradise. These are the 4 that are in there. We use Tahoma Bridge and Tahoma Vista to track events, especially as they're going down South Tahoma or Tahoma Creek here. You notice a lot of what we're doing is aimed at Tahoma Creek. It's only because Tahoma Creek is so active. So again, if we see an event in Tahoma Creek, we usually would see it in Emerald Ridge and Copper. If we see something in the Pyramid Creek or Couts Glacier or Couts Creek, we would see it between Copper and Mildred, and then you're kind of bookending these drainages here with them. We don't, again, monitor Tahoma Bridge and Tahoma Vista. I'm debating adding Puyallup River Rush and then Observation Rock, these 3 seismometers over here, to see if we can pick up other events that go on over here. We know that there's debris flows over here. We just don't have any way of detecting them, or at least, some of the new seismic networks will be able to detect them. But, it's really interesting just to think about, like, these debris flows that are going down. They don't affect park infrastructure, but we need to be able to know that they're going on so we can understand that and understand the history of what's going on. So this gets reported onto a console. The QR code will take you to this page. It looks like this. It's designed for a mobile device, so I can look at it on my phone, and it'll tell you the status. It shows you the view of what's going on. There'll be more of these kind of images coming up here in a second. It gives you a lot of data that you can kind of really quickly look at and see what's going on. So this is the result of the system since we put it in place this year. Again, we still have a lot of wind noise. We've had to adjust several things, several alert levels, just to try to filter out that wind noise. Some of these things I'll show coming up here. So I'll show what the wind noise looks like on these spectrographs here. We did see some organized seismic activity that occurred in July. It was really interesting. It lasted for like 6 to 8 minutes, but it didn't get high enough to activate the system. There was an earthquake that occurred about 50 miles from the park. It was a 3.8, which is a pretty intense earthquake for this area. So we changed that alert level from 2 to 2.5 minutes. We have the confirmed debris flow that occurred August 15th. Again, that was a max alert level of about 3. And it was a small debris flow, so it ended really between the suspension bridge and Tahoma Vista, somewhere in that range. But we did see hyper-concentrated flow downstream. Copper and Mildred did not reach an alert level on that one, but they did show activity. I'll show that in just a second. We did reach an alert level 5, but that was because people were stomping around the seismic station doing work. It was kind of funny. There's some more wind noise. And then this last weekend on Saturday, we had our first atmospheric river, and there was something that happened in Couts Creek. And obviously it was really rainy. We don't have the field crews to get out there, and only it was about 5 or 6 minutes long. So something happened, but we're not entirely sure what it was. Called these hydrologic anomalies. So kind of looking at some of these data. This is wind noise. This can trigger systems. So like what you're looking at here is the spectra. Here's your 2 to 5, 5 to 10, 10 to 15, 15 to 19, these 30-second bins. And then the top is the analysis of what we're seeing. So green is alert level 0. This orange color, or yellow color is alert level 1. So what it's looking at here is enough of these data points inside of this window that activated an alert level. And this is one of those things that's really hard to filter out. If you get enough organized wind over enough time, it actually will detect this. And again, this was actually, again, earlier in the day before this surface event was detected this last weekend, we did have wind noise activations. Again, Emerald Ridge, for some reason, is the station that has these kind of events. looking July 20th, this is that weird anomaly. It showed up on Emerald Ridge and Copper. So something in Tahoma Creek started here, worked its way downstream, and you can see it. Copper is a very quiet station. It's usually this dark blue all the time, and it showed up pretty strongly. I wouldn't say strongly. It showed up to a point that it was recognizable in these two seismic stations. You could even see it a little bit in Mildred Point. So something weird happened here. Very quiet, so very small event probably, but something definitely occurred there. Here's this earthquake that was, again, Mount Rainier is right down here. The seismic stations are here. The earthquake is up here, north of North Bend. Again, this is a 3.8 earthquake, 16-kilometer depth, 52 miles north of the park. So again, just enough shaking over enough time that this was 2-minute window. We changed it to 2.5 minute. 2.5 minute would have included this data point, which would have then not activated the system. So that's why we made that change. And then the big one that we had this year was the August 15th debris flow. You can see really clearly. I was in my office. My office was, I think, was 85 degrees. I overlooked a parking lot. It's really, really, really warm in my office. And I was just about to leave and got the text message. I looked over. You could see the seismic data, clear as day, debris flow signature. Just a short little debris flow worked its way downstream. This is, again, I think about 20 minutes or so on here. It showed up Emerald Ridge, showed up on Copper, but didn't activate because it didn't get that 15 to 19 hertz range. And then also showed up in Mildred too, which is pretty cool. So definitely something going on. We got to get up in a helicopter, basically went and very quickly requested the helicopter, and they were able to get us in the door towards the helicopter, and we went up and found this new channel right here, and you can see it's very clearly, very freshly incised, and this went quite a ways downstream, just to show you. Again, the terminus, there's, again, quite a bit of water coming off here. That channel I showed you was off over here somewhere. But again, you can see there was evidence of a high water mark in this river channel, and you can see some pretty good incision that occurred. So very clearly a debris flow that occurred in this channel. And then last kind of weird one was this event that occurred this weekend. Small enough to trigger Emerald Ridge to an alert level 1. I'm sorry, not Emerald Ridge, Mildred Point. So this is over on the Couts drainage. But again, something organized. Again, the filtering takes out all of the earthquakes. It takes out anything that's really not organized, and it puts it into this shape, and we can see something happened. I talked to Wes about it. Wes Salem, the USGS, thinks maybe it was a rockfall that was near Mildred Point seismograph. It could have been a very small debris flow. It's really hard to tell without actually being able to get out and look at it. But it did occur during one of the first atmospheric rivers to hit the area, and one of my seasonal one of the used to be seasonal new term employee Taylor Kenyon was in the park and was saying it was just downpouring in the park. So not really that surprising that we would see something like that before we start to get accumulations of snow in the park. So where are we at? Mount Rainier currently has a system to qualitatively forecast debris flows. It's pretty good, I think. It has a long way to go. I would solicit any ideas you have to improve this system. It's better than what was there before, I'll put it that way. So we have an improved and calibrated system to detect debris flows, and it even seems to work, which is a benefit. So, and there's an example of the text message I got on Saturday that showed me something was going on. So again, still a long way to go. I'd like to add additional stations. We're still going to be tweaking things around, looking for these events. And again, they're really, really hard to accurately forecast. So, and my predecessor, Paul Kennard, always had this great quote: "Mother Nature always bats last." Whatever we do, we can always anticipate that things are going to change as we go on. So we do have a couple weird little things that happen, and just want to point these out. Just kind of the events that shouldn't happen. We have occasional winter outburst floods that happen, and this doesn't make any sense to me at all. Winter outburst, when you have a ton of snow up high, you would not expect to see a surge of water that comes out of the glacier, and this is exactly what we saw. This actually ripped out our pressure transducer and carried it downstream somewhere. So somewhere in White River, this is on the northeast side of the park, somewhere there's a pipe with a pressure transducer inside it floating down the river. So I have no idea where it's at. But again, it's interesting. You can see the water temperature decreased and then the stage remarkably went up during this event. When we looked at the Emmons Glacier, sometimes you see these weird things going on here. This is from Ben Wright, who was up there doing a snow stake study, and found this scar, essentially, that there was a moulin up here, and then there's a scar that looked like water ran through this location. If you do the math on this, kind of the back of the envelope math, this is about the equivalent amount of 100 Olympic pools necessary, or 64 million gallons of water, to melt this much snow and to cause this feature here. So something happens occasionally in these locations, and I don't know if we could ever predict these, but just again, this is where Mother Nature is telling us that, yeah, you got this cool system in place, but I'm going to do an outburst flood in the wintertime, just confuse you completely. So that is all I have to show you. Again, this is the outlet of the South Tahoma Glacier on the August 2019 debris flow. We had a helicopter pilot who was not scared to get us close to it, and you couldn't pay me money to hang out beneath that glacier right there. So I would love to hear any questions that you guys have. Thank you.